And they basically come up with a scheme, and the scheme actually works pretty well. Whenever you take something that's diverse and as things that happen in biological system, and you try to categorize, there's always exceptions. But their regulatory or their classification system actually seems to work pretty well. So if we talk about nomenclature, enzyme nomenclature. Take the chemical reactions that occur in a cell and basically break them down into 6 different classes. These are known as EC classes, and within each of these classes there are a whole bunch of subclasses, and that's what this nomenclature committee does, is basically if you find a new chemical reaction and a new enzyme and you want to classify it, so if there's okay, it's this class and this subclass and this subclass. We're just going to look at the major classes here. And the first one is oxidoreductase. And these are enzymes that catalyze redox reactions, the transfer of electrons from one molecule to another. Example might be one reaction anybody did any sprinting or anything like that this weekend? This reaction might have gone pretty well. This is pyruvate. We'll talk about this in metabolism. And if you add some electrons in form of a high energy electron carrier, this is carries it in the form of a hydride, basically. It'll transfer that electron and generate a reduced version of pyruvate, which is known as lactate. Lactate or lactic acid. So, for example, if you're sprinting, you end up accumulating, glycolysis is going at a high rate, but in general, pyruvate, the oxygen supply isn't sufficient to be able to drive the consumption of pyruvate. The gas cycle electron transport chain, so it accumulates. So to allow glycolysis to continue, it basically gets converted to lactate. And then the other thing that you end up with is the oxidized form of the high energy electron carrier, which is NAD. Now, to make a stoichiometry work, you actually have to add a proton into it. So the point is that there's an electron transfer between NADH and pyruvate. This is an oxidized molecule. This is a reduced molecule. And you end up having now a reduced molecule and an oxidized molecule over here. So electron transfer. So there's a lot of, metabolism is fundamentally an oxidative process, and there are a lot of redox reactions in metabolism. The next major class are the transferases. These basically transfer a functional group from one molecule to another. An example is the first enzyme of glycolysis. You see, I'm fighting that to pull it, get them the capital. I love these guys. Here's the structure of glucose. And that glucose, say, goes into a muscle cell, and you want to break that glucose down to get energy. The first reaction is you add an ATP. Remember, this has 3 phosphates, and you transfer a phosphate from the ATP to the glucose. Make glucose 6-phosphate. And you end up with ADP with phosphorylase. So you transferred a phosphate to the, basically a phosphate gets transferred. All right, I could give some enzyme names. This enzyme is hexokinase. And actually that brings up a point. A kinase is a transferase that is specifically, that transfers a phosphate from ADP. It phosphorylates the molecule. So it's sort of a subclass. I bring it up because it's a very well used term. Second kind of procedure where I should mention the name of this enzyme is lactase dehydrogenase. It's actually named for the reverse reaction. This reaction is a very reversible reaction. And you do a purification of that enzyme. And purification is, let's see, 162. Do you purify that or you do the kinetic analysis of it? I can't remember now. Has anybody gotten to in 162 gotten to lactase dehydrogenase? I think that kinetics probably would get into kinetics. All right, the next one are hydrolases. Okay, and these are enzymes that catalyze the cleavage of a molecule by the addition of water. And we've already talked a little bit about these things in terms of proteases. So hydrolases cleave molecules by adding water. Our example is a protease. And if we have a peptide bond we add water, we'll cleave that desktop. So this is trypsin and chymotrypsin that's in our digestive system, breaking down the protein. But it also could be, we haven't really talked about carbohydrate structure, but if we have starch or glycogen, those are also long chains of sugars, and you can break those chains by adding water. The next one are probably the most challenging to recognize. Those are the liases. And this is a group elimination, so it's an elimination reaction. Form a double bond or ring. An example I'll have, because it also kind of shows how difficult it is to see it, is another enzyme of glycolysis. So there's a molecule, you guys remember from organics, the Fischer projection. This molecule here is about midway through glycolysis or so. It's fructose 1,6-bisphosphate. And what we're going to do is we're going to cleave this molecule right across here, but in the process, actually generate an aldehyde. So what we end up doing is make these two molecules here. And the way you can think about this is we've actually created a double bond. It's basically elimination. We're eliminating this hydrogen, and we're eliminating this group here to form that new double bond. So the elimination reaction occurs here. So here's our new double bond. This enzyme is known as aldolase. So and there'll be some problems. When we get to the homework for this chapter, there'll be some problems where you have to classify different reactions according to the reaction type. And those are the most challenging ones to really kind of look at what's going on.
So the way to distinguish lysate from a hydrolase is for the hydrolase you need to have water.
That's right. Hydrolase is going to add water. Here, we're just splitting it apart. It's an elimination reaction. We're just splitting it apart. a isomerase. Isomerase is our, it's pretty straightforward. It's kind of like molecular rearrangement. Since we're kind of talking about glycolytic enzymes, there's another glycolytic enzyme. Here's glucose, the thicker projection for glucose. Actually, it's in the glucose 6-phosphate. Okay, so now what we're going to do is we're just going to rearrange it. This is actually, we're getting into the carbohydrates a little bit. So we should have seen some of this in organic, but this is an aldose. This is an aldehyde up here. We're going to rearrange it to a ketose. This is going to be have a ketone here, and so we're just going to go. This is now fructose 6-phosphate. And again, these both have the same molecular formula, same number of carbon, oxygen, hydrogen atoms, and all of that. We're just rearranging them. So that's what makes it isomerase. This particular enzyme is known as fructose. No, is hexose phosphate isomerase. All right, now we get to the last one. I know this is just kind of like cranking through, but at least you see, and I don't know, as we talk about different enzymes and what goes on, like it's flat. Put it in our little color here. The next one, and this is our ligases. And this is bond formation coupled to ATP hydrolysis. And where we really see this a lot is in enzymes involving nucleic acids, particularly building nucleic acids and working through things. This is also, they're also known as synthetases. And so synthetase, you'll see a lot of enzymes called synthetase, and if it's synthetase, it means ATP is involved. If it's a synthase, ATP is not necessarily involved. So that's a subtlety that you'll like to look out for. So an example is a DNA ligase. Those of you who've been in molecular biology, they talk about ligation reactions all the time. And we haven't gotten the nucleotides, but basically if you have a sequence of bases, at the 3' end you have a hydroxyl group, and then you have a phosphate with 5' end, and you might have a DNA ligase will use the energy from ATP hydrolysis to join these together. We also get rid of that phosphate too here. You join, so you have a couple of nucleic acid strands, you join them together. All right, so that's good. We've done that. We've done our due diligence, walking through this classification here, so as we get through different enzymes. Now, the final sort of introductory point before we get into the meat of catalytic mechanisms is to talk about enzyme cofactors a little bit. So far, when we've talked about proteins and protein structures, we're really focused on the amino acid chain and folding up and continuing the structure. In fact, often there are other molecules that end up getting incorporated into the protein to help in the protein's function, and in particularly to help in its catalysis. These are known as cofactors. And so we'll basically, let's talk about those a little bit. You know, when you think about the 20 different amino acids, and you think about the functional groups in the 20 different amino acids, and generally, you know, you've got an alkane, which isn't particularly reactive. You've got an alcohol, so the serine or threonine will provide an alcohol, or even if you want a little bit more acidic alcohol, tyrosine will provide an OH group. What else do we have in there? Sort of our toolbox in there. We have an amino group. If we need an amino group, we can get a lysine. And then we've got the funky guanidino group and arginine, if we want that. We've got that imidazole group. It's good for acid-base reactions, where because it can be the protein agency protein. What else do we have? We got this alcohol. Alcohol. Notice there's no aldehydes. There are no aldehydes in the side chains for amino acids. And that's because aldehydes are very reactive, and so particularly to amino groups. So basically, if you have a protein full of aldehydes, it's likely to sit there and just react with itself like crazy. We got the carboxyl groups, you know, in aspartate. We got the amide, if you need an amide nitrogen in there. Okay. But that's a relatively limited toolbox for all the different chemical reactions. So a lot of what a protein just does is borrow another molecule to get the functionality of that other molecule. So these are known as cofactors. A lot of them are metal ions. And they can either be be really tightly bound to the enzyme or relatively weak bound to the enzyme. A lot of them actually come in not necessarily by binding to the enzyme, but are involved in the reaction by binding to the substrate. An example of these are all these enzymes that use ATP as a substrate and involve ATP hydrolysis. It's really not ATP that is actually binding there, but ATP complex with magnesium or manganese. That within the aqueous environment of the cell, a lot of the ATP is actually not free ATP, but is actually complex with a divalent metal cation like magnesium and manganese. And those actually then, it's that complex that actually binds the enzyme. But the presence of the magnesium and manganese is very important. So magnesium, manganese, common reactions involving phosphates. Transition metals, these are common in redox reactions. They basically provide an electron carrier in there. Some of the most fundamental reactions in biochemistry, I'm thinking of reactions that occur at the photosynthetic reaction center, where you're actually generating oxygen, the oxygen evolving complex. Or, for that matter, in the mitochondria, the final reaction of the electron transport chain, where you actually consume oxygen and generate water. These are the basic enzymatic reactions that really drive all of life, right? The photosynthetic reaction center creates reduced carbon for all us heterotrophs to be able to get, and then we get the energy out of that reduced carbon from this electron transport chain. Some of those most fundamental reactions, really the protein is just holding a complex of metal ions. It's all metal ion chemistry that's actually going on there. We've had a discussion in terms of the curriculum for biochemistry, is whether or not for our BS biochemistry today we could actually require inorganic chemistry. And I'm actually kind of pro that. I dropped something else out, but I'm kind of pro that, because really the most fundamental biochemistry is really inorganic chemistry. And the organic chemists, like to write a lot of claims to it, but really, so a lot of those fundamental reactions are inorganic chemistry. And all that protein does, all those organic molecules, is basically just hold those metal ions in the right place, in the right structure. Okay, so metal ions, we can also have small organic molecules. And these are known as coenzymes. And we can find, there are some that are like transiently associated with the enzyme. That basically they're almost like co-substrates. These are really co-substrates. And it's actually, the starting over, if I was a biochemist, I wouldn't even call these. An example of this, we did it when we talked about our remember the NADH, we were talking about the oxidoreductase? We were taking pyruvate to lactate, which required NADH. NADH is commonly known as a coenzyme. It's not really a coenzyme because it's really just another substrate. It's another reactant in the reaction. But a long time ago, people basically started calling those coenzymes, and so it got the reference became a little confused. So the example of this again is NADH, and the other reason it's a little bit confused because most of these things are a catalyst, right? What's the property of a catalyst is that they're not consumed in the reaction. They accelerate the reaction, but they're not consumed in the reaction. But NADH actually gets consumed in the reaction, and it requires regeneration. So I guess what I'm trying to do is be up front about how the nomenclature of coenzymes is a little bit messy, and it's basically due to historical. Then there are those that are more tightly bound to the enzyme. And what I mean tightly bound to the enzyme is that if you took the enzyme and put it in a dialysis bag and then dialyzed all the small molecules that are surrounding the enzyme, dialyzed it away, that these tightly bound things would stick with the enzyme. They're bound tightly enough they wouldn't come off the enzyme and stay inside the dialysis tube. Sometimes they're covalently attached, sometimes they're just really tightly attached by a lot of non-covalent. These are also known as prosthetic groups. Example is pyridoxal phosphate. Which actually this molecule here provides an aldehyde. I'm going to show you the structure of these. I didn't bring that those particular slides. I didn't load them up for today, but I'm going to show you those on Friday. Often the final point I want to make about these enzyme cofactors is that they're often vitamins that is required in human diet. Now, we don't actually make these enzyme cofactors, but we get them in the diet and they're found. All right, I think actually that's a good place to stop. I'm trying to let you guys out.